Hey there! In this video, we're going to talk about linear contrasts, which are probably something that you've heard about, but maybe aren't using to their fullest capacity in JMP. Now to do this, we're going to look at the US demographics data set, which is a pretty basic data set. We have states and we have a number of quantitative variables like 8th grade math, population, and then we have some categorical variables like region. And so what we're going to do with linear contrast is figure out differences among the levels of our categorical factor. And so in this case, if we wanted to say compare the 8th grade math scores for the South versus the West. Now you can do this in a number of ways. And of course, you're probably familiar with things like student t-tests or what you would do following an ANOVA. But a linear contrast is going to enable us to do some very special things. So let's first take a look at how we're going to get to using a linear contrast. And then we'll talk a little bit about what they do, a little bit about the math behind them, but then really about the application of them. So to start, we're going to use fit model. Fit model is the only place in JMP where you're going to be able to do a linear contrast. And in fit model, what we're going to do is specify a basic model. We can do it as a simple one-way ANOVA to start. So we'll predict 8th grade math, let's say, on the basis of region as our model effects. Now for convenience, I'm going to set the emphasis to minimal report just to keep the rest of the output suppressed. You can of course run a linear contrast anywhere you want in fit model with any emphasis you like. This is just the type of output that's shown by default. So I'm going to run this model. We'll get our basic output, and you're going to find the linear contrast option under the effect details section. And it's going to occur under the red triangle next to a categorical factor. And so in this case, region, these are categories, they're levels of a factor. And one of the options under the red triangle you'll see is this least squares means contrast. Now, before I go into showing you this, let me back up and say again, if you wanted to simply compare the levels here, South versus West or Northeast versus South, there's plenty of ways in JMP you can do that. And one that is probably familiar to you is the least squares means students T. And I'm actually going to run this because I want to make some comparisons or callbacks to it as we show the contrast. So let me run the students T. I'm going to turn off the crosstabs report. I'm actually also going to turn off the connecting letters report, and I'm simply going to turn on the ordered differences report and the detailed comparisons. Now these will really show the same things. The detailed comparison simply shows a lot more, obviously details, and the ordered differences simply shows the p-value. But I want to actually have the t-ratio available here, and so we'll look at these a little bit later. And I'm just going to minimize these comparisons. Now you'll see there's a lot of different pairwise comparisons we can make, each level compared against each other level. And that is something really you often want to do in the context of an ANOVA, after you found that there is a statistically significant difference, in this case, among regions for 8th grade math. We might want to say, where are those differences? Where do they emerge? Now, I will say the least squares means students T. We didn't protect about alpha escalation. That is your overall false alarm rate or your probability of making a type 1 error across the set of these comparisons. Let's ignore that issue for now. There are ways in JMP to control this, like the 2-key HSD. But right now, let's just think about these comparisons without the extra statistical issues here that we certainly should be aware of and consider. But for now, let's just think about the actual tests. So we have these comparisons. Now, what if you wanted to do this through the least squares means contrast panel? And I say panel because when I turn this on, you'll notice that I get a little panel here where I can essentially specify comparisons. And you're going to do it with a pretty simple rule. And we're going to do that with these little pluses and minuses. And the rule that contrasts abide by is that the sum of the contrast weights, the weight is what we're eventually going to put in, they're all at 0 right now. The sum of the weights will be 0. That is, we'll have a balance of positives and negatives. So I'll just do one for you right here. I'll click northeast as positive and west as negative. So the sum of the weights is 0. That is, they balance out on the left and the right. And the other rule is that the sum of the absolute value of the weights, so if we ignore the negative and positive sign, is 2. Now, when we're simply comparing one group to another group, it kind of makes sense. We have a positive 1 and a negative 1. We're not going to talk about what it does yet, but watch what happens when I add another positive and another negative. They all change to 0.5. JMP automatically constrains that the sum of the absolute value of the weights will end up being 2. Don't worry about why. We'll talk a little bit about the math, and I'll show you some formulas later. But that's just something that JMP will enforce and do automatically for you. So I'm going to take those away by clicking the opposite sign. So I've clicked a plus for the negative one and a minus for the positive one. Okay, so we're back to the Northeast having a weight of 1 and the West having a weight of -1. Now what this literally means is when JMP figures out the value of this contrast, it's going to take the linear combination of our means applying these weights. So it will take the mean for the Northeast times +1, which is just the identity, and the West mean times -1. So it'll be the negative value. It'll take the sum of those two, and that'll end up being the difference between those two means. How different in 8th grade math is the Northeast from the West. So this contrast I'm basically defining a little detector. Where do I want to detect differences? And the magnitude of the difference is defined by the sum of those weights, or really by the linear combination of the weights applied against the means. So watch what happens when I click done. JMP's going to produce a little test report here. We have sums of squares. We'll talk about where those come from. Degrees of freedom. We can talk about where those come from in a second too. An F ratio and a p-value. Look at this p-value for a second. 0.0481. Now, do you see that anywhere else in my JMP report? Well, we're comparing, in this case, it was the Northeast with the West. Let's go to that least squares students mean report and look at the Northeast versus the West. Well, we have the same p-value. This is the same test, but found in a different way. We're not doing it as a t statistic, we're doing it as an F statistic. That is, we've actually come up with a least squares means contrast, and that's defined as an F. If I expand the test details, you can see there's more details here. There's an estimate of that contrast. Remember, that's what I said when we do a linear combination, the weights times each mean and then summed across. Well, 5.2581 is the difference between the West and the Northeast. If we see it's there too, 5.2581. So nothing really magical has happened here. I've just defined a test using a contrast. That is, I've defined a test with these little pluses and minuses as a way to find, where the differences are that I'm interested in. Now, if you notice, there is a t ratio produced in the test detail. If I expand it, 2.0305, that is the same t ratio as if I go to the West versus Northeast here. So 2.0305. It also happens to be the square root of the F ratio. That's just something you can get to if you like using some math. So what we've defined here is a simple test comparing one level against another level. Now, if we wanted to produce all pairwise comparisons, doing it through a least squares means students t, that option is pretty darn convenient. JMP will produce all those tests for us. So why use a contrast? Why go through the trouble of defining a little detector using that contrast panel when clearly JMP can produce all the pairwise comparisons and we can see that they're already equivalent? Okay, this is where contrasts become useful. So let me minimize some of this output and let's consider a slightly different test. So I'm just going to minimize that existing contrast. We can add as many as we want. What if I wanted to compare not just the West versus the Northeast, right? Those are two of the levels. What if I wanted to compare the average of the South and the West, consider that as one region, against the average of the Midwest and the Northeast? So I wanted to take that as another sort of section. So what I'm doing is, you can imagine recoding the data in the data set. Let's group those two groups together, come up with a new value, and then take a mean comparison. We can do that. It actually won't be as statistically efficient for some reasons that we don't have to get into here. But the short reason is that if we combine or lump together those two groups, the variances within those groups will be larger, and larger as a factor of how much those means differ within the groups. We're lumping together individuals that are really different if we think the means are different. So what we can actually do with a contrast is taking in all the efficiency we gain by estimating the variance in the population with those groups separated. We're going to be able to combine the means and compare those means, but while using a pooled estimate of the variance in the population. Don't worry about all the details of that. JMP does it for you in the background. But let's see how we would do it using the contrast panel. So I'm going to go back to the region red triangle. I'm going to grab least squares means contrast. And you saw me do this before. I can actually add weights to multiple levels of our contrast. So what I can do if I wanted to find this, let's give positives to the Midwest and the Northeast, and let's give negatives to the South and the West. So now we have 0.5, 0.5 as the weights for those two, and for the South and the West, negative 0.5 and negative 0.5. Again, remember the rules. The sum of our weights adds to 0, or sums to 0, right? So they're balanced on the left and the right, and the sum of the absolute value of the weights sums to 2. That is, if we just ignore the negatives and positives, they add up to 2. Okay, let's click OK or click Done. Now this test is comparing specifically those means we defined. Let me expand the test detail so we can remind ourselves of the weights. And just to give ourselves a visual, let's turn on the plot here. So what I did was lump together the Midwest and the Northeast. You can see because those have positive 0.5s. And we're comparing essentially the average of those two groups against the South and the West. So what we've done is defined a contrast that is a combination of those different means. We didn't have to do any recoding. We didn't have to tell JMP anything special. We just told it to define a little detector, a little contrast that picks up on those differences. And that's a pretty powerful use of a contrast. Before we go into anything else, let's take a slight tangent into thinking about how this test would have worked if we had done the recoding. And I said it's not as statistically efficient. And just as a quick demonstration for us, let's go back to our table. I'm going to right click on region and recode. And let's actually pretend like we're going to group these. So I'm going to say group Midwest and North to group 1 and group South and West to group 2. Because let's imagine we were going to do this, using our recoding method. And I can actually go and let me just do this as fit y by x. Take region 2, comparing 8th grade math. There we go. And just so we get the same F statistic, let's do this as an ANOVA. It's the same as doing a t-test in this case, but let's just do it. Notice we get 16.6194 for the F ratio versus 16.5530. Okay, trivially different. Our p-value ends up being the same numerically, at least to 4 decimal places, but it's not. So there is a difference here, and the difference lies in the mean square error. There's no difference in the comparison, the magnitude of the difference between these groups. If I actually expand and we look at the estimate here, 7.2929, that is the mean difference between these two groups. The mean didn't change. It's the estimate of the variance. Again, what we're doing on the right-hand side is estimating the variances of these individual levels of region independently and pooling those sums of squares to get an estimate of the population standard deviation or the population variance. On the left-hand side, when I grouped those two levels, JMP doesn't know that the individuals coming from those two levels actually are coming from 4 groups. It can't pool the sums of squares independently. And so it's just taking the deviations, if we look at it up here, the deviations of all the individuals to that grand mean within group 1 and all the individuals to that mean within group 2, pooling those sums of squares and then estimating the population variance. The short story is that your mean square error, we find it here, so root mean square error, or we can look at the mean square error under the analysis of variance table, 40.126. That 40.126 over here is going to be larger than the mean square error, 39.954. So there is statistical efficiency by not just lumping these different groups of individuals together to get that comparison. The statistically correct way, the most efficient way, is going to be doing the contrast. Now in this particular comparison, or this particular example, the difference was trivial. But that's only because the individuals in these two groups aren't very different on average. That is, the Midwest and Northeast are kind of having the same mean anyway, and the South and West kind of have the same mean anyway. And so lumping them together didn't change in that big of a deal, the actual mean square error. Okay, so that's a slight tangent, but notice that the contrast gets us to a result that is actually statistically better and statistically correct, and where it's enabled because we can define those contrasts in very specific ways. Now for the next example, we're actually going to have to pop over to a different data set. And to do this, I'm going to open the data set analgesics. And so I'll just go to the sample data here. Let's open the sample data directory and let's find analgesics. And this is a nice data set because it kind of mirrors the idea of doing a factorial analysis of variance. And so what we have here is gender, drug, and we have pain. And what I want to show you is that we can do a couple other things with contrasts, or that contrasts are really the root of how a lot of the analysis of variance is working anyway. And so let's set up our model. We're predicting pain as a basis of the full factorial of these. So we have a main effect for gender, a main effect for drug, and then we have the gender by drug interaction. I'm going to change it to minimal report again and click run. All right, so when we're doing a factorial analysis of variance, one of the things a lot of times we're interested in is that interaction term. And so if I expand the effect details and let's just turn on the plot and let's create an overlay and let's do drug. And so what we have here are separate lines for the men and for the women, and we're looking at the difference between the drugs, A, B, and C. And that interaction is actually something we care a lot about. We're caring whether there is evidence that the pattern of effects here for men and women differs for the different drugs. Now, sometimes it happens when we have 3 levels, A, B, and C of these drugs. Maybe A is the control drug, that is something that actually shouldn't differ by men and women. But B and C are the drugs that actually we're testing. So there may be a situation where we want to test the interaction, but eliminating one of those levels. We just want to do an interaction testing the difference between B and C for men and women. Now, we could just remove A from the data set. That is, we can actually exclude those rows, rerun this analysis, and get interaction that looks at just B and C. And just so we can see that happen, I'm going to grab the A's, select matching cells, let's hide and exclude, and let's produce the exact same. I'll just recall it here. And let's actually show the interaction. And so that interaction under effect tests or details, let's do the same thing. So now we're looking at just the effect for men and women for B and C drugs. And so we could do it that way. That is removing some data from the data set. Of course, we're removing all the A's. But that interaction term, 0.8699, that is our test of, is there evidence that there's a different pattern of effects for men and women just looking at drugs B and C. So I'm going to actually put those rows back in the data table. On the left-hand side, you might suspect there's going to be a way we can do this as a contrast. And the way we're going to do it as a contrast is to mimic the idea of what an interaction test even is, but doing it as a contrast. Now, the way an interaction test works for a 2x2 is actually pretty straightforward. It's the difference of the differences. That is, how different are men and women for drug B, and is that difference, that magnitude of difference, different from the difference between men and women for drug C. It's a difference of differences. And for a 2x2, two levels of each factor, it ends up being a kind of a simple contrast. So that's the example I'm going to show you. If we go to the left-hand side, pull open our trusty contrast panel, again, under your factor effect, red triangle, the interaction term is actually going to be definable using this contrast panel. So remember, we're just interested in, for drug B and C, whether men and women differ in terms of the pattern of their effect. Or said differently, is the magnitude of difference between drug B and C, between drug men and women for drug B, is that magnitude different from the magnitude of difference for men and women for drug C? And we can kind of see that it's not. The lines are parallel. The difference between them is pretty much the same. Okay, so how are we going to define this? Well, it's the difference of differences. So let's look at how we would define this on a contrast panel. Let's define the first difference. So between men and women for drug B, so I can say for female versus male for drug B, let's do positive, negative. And then I want to compare that to the difference, so switching the signs between men and women for drug C. And so for C, instead of giving it a positive, I'll give it a negative. And then for male, for C, I'll give it a positive. And so switching the signs, because I want the final estimate of this to end up being a linear combination of those means, such that the value at the end is actually how different are those differences. And so all I've done is just flip the signs on one. So let's click done and see what I get. Well, 0.8231. That looks pretty familiar. We have 8699, 8231. The difference in those p-values is simply because on the left-hand side, we're using the data from group A or from drug A to still estimate the population variance. We get statistical efficiency because we haven't removed data. Now that's a viable thing to do, and it is the most statistically efficient thing to do if we really believe the homogeneity of variance assumption is upheld. That is, that the variance within all these groups is actually estimating the same population variance. If that's been violated, then all bets are off. You should probably do it as a true subdesign, removing the data. So that's a different conversation. But the idea is that you can define that interaction using a contrast panel. It's literally the difference of differences. And to do that, you're really just entering in positive, negative, negative, positive. You're flipping the signs so as to make that comparison. All right, so that's replicating an interaction term by doing that. You can also replicate all sorts of other things. So if we look at the main effect for, let's say, drug. Let me close this on the right-hand side. So the main effect for drug here, if I open up the plot, notice that we have three levels. And so if you think about it, there isn't a single contrast that's going to be able to capture all the degrees of freedom in statistical terms, or all the differences, just in general parlance, among these different means. It actually is going to take a few little detectors, because A can differ from B, and A can differ from C, and B can differ from C. Now let's pause for a second. Let me go back to the effect tests section. And there's this degrees of freedom. It's really the degrees of freedom for the numerator. That's going to give us a clue here. This is how many detectors, how many contrasts is needed to actually pick up all the differences that can exist. And if you know a little bit about contrast, may know about difference contrasts or Helmert contrasts. There's these special types of contrasts that define what are known as orthogonal sets. Sets of contrast where the detectors don't pick up the same differences. So they're not detecting or sensitive to the same types of patterns in the data. So drug here, degrees of freedom for the numerator is 2, which means we need 2 detectors in order to pick up on all the differences that can exist within drug. Okay, so let's look at how we might do this. If we just think naively about it, the differences can exist between A and B, and A and C, and B and C. But if you think about it, once we know how much A and B differ, and how much A and C differ, we're going to be able to figure out how much B and C differ. So we really only need 2 of those comparisons. I'm going to use A versus B and A versus C as my set of detectors. And so let's actually go to the least squares means contrast panel. Let's see how we're going to enter this. I'm going to do one detector for A versus B. So -1 and +1 as those weights. I'm going to click new column, which is going to give me another degree of freedom, another detector that I'm going to sum together in this final test. And I'm going to say A versus C and click done. So this is my 2 degree of freedom contrast. I put in 2 little detectors, the estimate and the sums of squares, how the magnitude of really the differences I'm picking up on. It's paying attention to 2 of those differences. And hey, look, it should match. And let me minimize the right things. Here we go. Let's minimize that contrast. Go back to drug. And there we go, 0.0227. Well, look at that. That matches my main effect of drug. And the degrees of freedom, 2. Denominator degrees of freedom, how many degrees of freedom for air I have. That's still the overall degrees of freedom for the table. And the F ratio should match 4.3713 and 4.3713. I've built the same test just using the actual contrasts. So if you look up these different types of orthogonal sets of contrast, you can absolutely just come up with the same main effect test that JMP does for you. There's no reason to. JMP does them for you. But the flexibility to specify all sorts of variants of those types of tests becomes incredibly powerful. It also means you can do very special things like picking up linear trends or polynomial trends. You can define trends across categorical levels if you really believe they have some, dimensional underpinnings that are, equally spaced. And so if you look up polynomial trends or polynomial contrasts, there's orthogonal sets of those. So you can define all of these using that contrast panel. So pretty powerful stuff. Okay, let's do one final example of something you can do. And to do this, I'm going to go back to that US demographics data set. And I'm going to set up something similar to the model I did before, but not exactly similar. What I'm going to do is I'm going to take, let's predict still 8th grade math. That's great. I'll still use region. But let's control for or create a model where we're also taking into account the smokers in the state. I'm just picking this naively, I'm not sure why. But let's turn on minimal report, and I'm going to keep the dialog open here, and let's see what we get. I haven't tried this one before. Okay, so good. We have a little bit of difference between the lines. That's what we want to see, at least for the purpose of the example here. I'm going to minimize a bunch of things. And let's, before we go any further, talk about what this model is doing. This model is using smokers to predict 8th grade math and region to predict 8th grade math. And there's no interaction between the two. So this is a proper ANCOVA. It's an analysis of covariance, which answers the question, what if these particular regions didn't differ in how much they smoked? How big would the difference be between them in terms of their region differences? And so we're controlling for smokers across region. And the whole reason to do an ANCOVA is because we think there is something in 8th grade math that is explainable on the basis of smokers, and we want to remove that extraneous variance from the response from 8th grade math before we try to test for the differences among the regions. And so it becomes a very statistically efficient model. But there's a big assumption within ANCOVA, which ends up being known as the homogeneity of regression assumption. We better believe, or we better have some reason to think, that the relationship between 8th grade math and smokers is the same for all the regions. And there's a really easy way to test for this. We can take smokers and cross it with region to give us a term in the model that actually tells us, do we think we have evidence that there's a difference in that pattern? And if we look at this, I'm just going to, again, minimize the same things. And let's just look at our effect test. the interaction between smokers and region isn't statistically significant. This is a fairly smallish data set. But if we're just looking at the plot, let's pretend that we have reasonable confidence in this result. We can see there is some differences between the regions in terms of the relationship of smokers in 8th grade math. In some region, the relationship is stronger than in other regions. And so if this is a pattern you see in your data set, well, you shouldn't be using a proper ANCOVA. We shouldn't force the model to have just one slope parameter for actually all the different regions. All right, that's not the actual point of this video. We want to talk about doing a contrast in the context of doing an ANCOVA, or on the right-hand side, really an indicator variable regression with an interaction between the categorical variable and the continuous variable. Don't call it an ANCOVA. The ANCOVA is the one on the left that does not have the interaction term, because that's the assumption of the ANCOVA. But we'll just say it's an ANCOVA-like model for simplicity here. So on the right-hand side, for the ANCOVA-like model, what would a test between the regions look like? Well, if we look at it and go under a region, we see all our familiar options. We can do a least squares mean students t, and I'll just do this for ourselves for now, and I'll get rid of the same output I did before. I'll turn on the order differences report. So we're doing tests here between the different regions, but we're doing tests at a particular level of our continuous variable. We're doing it at the mean of smokers. That's what these tests are really saying. What is the difference between the South and the West, for instance, at the mean level for smokers? Because if you think about it, in a model where we're allowing there to be a relation between smokers and 8th grade math, if we were trying to make a comparison somewhere other than the mean of smokers, the difference between, let's say, the South and the West, that's the blue line and the orange line here, right? If we're doing it at a high level of smokers, that difference is going to be very different than if we're doing it at the mean. So notice that we have to pay attention to at what level of smokers this comparison is being made. On the left-hand side, in the actual ANCOVA model, it doesn't matter. Because these lines are all parallel, the difference between the blue and the orange lines is the same at any level of smokers. So there isn't really a question of that. But in the model where we're allowing an interaction, there's a vast difference between the blue and the orange lines at different levels of smokers. So the least squares mean students t is just saying do it at the mean. Ignoring smokers, what's the difference between those two groups? Now, it's in the context of a model where we're taking into account the relation between smokers and 8th grade math, so the variances are being absorbed a little bit with that relation. But principally, it's the same test as if we didn't have smokers in the model. But what if we were interested in the test of those two regions at a different level of smokers? Well, it might not surprise you, given the context of this video, that you're going to be able to do that through a least squares means contrast. And so let's actually try it. Let's go to the region, turn on the contrast panel, and notice we get something new. We actually can specify the South versus the West, but we can type in a value for smokers. 21.008, you might guess, is the mean, but let's try it at a different level. Let's try the comparison at maybe 15 for smokers. And so I'll type in 15, click done, and there's a p-value. Let's try it again at, let's say, very positive. So we'll do 25. So let's go back, least squares mean contrast. Let's do South versus West, and let's do that at 25. All right, so we have two different contrasts here, vastly different p-values, obviously. If we look at the estimates, so I'm going to expand the test details. The estimate for the first was 13.33, and the estimate for the second, negative 6.59. Okay, let's go back up and look at our plot. Notice why that is. For the first test, our South was above, in this case, the West, and in the second case, it was below. So it is literally paying attention to what we dialed in there for smokers, as you might imagine, given that we typed in a value. And so when you're in a type of model where you have that interaction, and it matters at what level of the quantitative or continuous variable you're at, that's where you're going to be able to make that comparison. Now, there was actually a post on the community a while ago that actually asked, how can we test in this type of model whether the intercepts are different between the two different groups or any of the groups? Well, if you think about that, an intercept test is just when the continuous variable is at 0. And so if I go to my region, let's do a contrast, and let's compare the South and the West, and let's put smokers at 0. So this is now a test of the intercept. Is the intercept of those two lines for those two different regions, are they different? In this case, 0.0496. So you can actually get to that intercept test now simply by going into the contrast panel and specifying 0. but a lot of power here. And again, the basic principle is that you're defining these little detectors that are allowing you to pick up on differences in the data. And so we looked at just a few, but know that that's an option for certainly these models and lots of others. So hopefully this helps.